Today we will be discussing about regulated power supplies which are required for maintaining a constant output voltage at the load side. In the earlier class, when we were discussing about the rectifier circuits using diodes, we have seen the application of the rectifier in the power supply, because when you have an AC voltage at the input, the rectifiers are used to convert the AC into DC voltage, and by use of filter circuits using capacitor filter, we have seen that the ripple present in the output voltage after rectification was reduced, and that output voltage from the smoothing circuit or the filter circuit after rectification is supposed to be a constant DC voltage which is fed to the load. But now there are various reasons because of which the output voltage or the voltage at the load side does not remain constant. So there is the need for a circuit which can regulate the output voltage at a constant value. Now this type of circuit which is used in regulated power supplies is an electronic circuit that is designed to provide a predetermined DC voltage. This DC voltage is independent of the current drawn by the load from the DC voltage, and it is also independent of any variations in the AC line voltage and also in any change in temperature. Now how the output voltage is affected by any change in the AC line voltage as well on the current drawn, how it is dependent, as well as temperature change. Now we have seen in our domestic power supplies that we use in our houses that the line voltage does not remain constant. There is fluctuation in the AC line voltage which is supplied to us. Although it is supposed to be 230 volt, it's never supplied at that voltage, and sometimes it so happens very frequently that there is fluctuation in the AC line voltage. So because of the line voltage having these fluctuations, the effect will be the output voltage that we are using for our devices in our houses, that also will have a variations in the voltage supplied to them, and that is not desired because these fluctuation in the voltage being given to the household gadgets may damage them. So it is required that we get a constant DC voltage even though the input AC line voltage varies. Second factor which affects the output voltage at the load side is the load current. If we have a variation in the load current drawn from the supply voltage, that also changes the output voltage. Another factor is the temperature. Because of the temperature variations, the regulator circuit, which generally uses electronic components like transistors, are affected. So the change in temperature affects the operation of the electronic components in the regulator circuit, and because of that also the output voltage does not remain constant. So we have to now find out how we can maintain a constant voltage at the output, and for that the regulated power supplies are used where there is a regulator circuit which can maintain a constant voltage at the output even any of these factors which I described just now is there. So even in the presence of any of these or all of these, the output voltage is maintained at a constant value by this regulator circuit. So today we will be discussing about some of these regulator circuits, and we will see how the regulation of the output voltage at constant value is maintained. Now again we go back to the block diagram form representation of a regulated power supply that once we just touched upon while discussing the rectifier circuit in using diodes. So if we look into the block diagram representation of a regulated power supply having different components in between, or in different stages we will be having different devices like shown here. So what is done is that we are having an AC supply voltage which is supplied by the electricity authority, that is given to us in the AC form, and it is a high voltage. So we have to first of all step it down to a level which can be handled by the rectifier. So that is done by using a transformer. So that step down transformer which is used to step down the AC input voltage to a voltage which can be handled by the rectifier, that is done here by this block which is a transformer. So first of all the input voltage which is an AC voltage, this is the AC input. So this voltage is having a high peak value. So using this transformer we will be first stepping down this voltage, and this reduced voltage is fed as input to the rectifier. And a rectifier which we discussed earlier, like half wave rectifier, full wave rectifiers, these are used for rectifying the AC input to convert it to DC. So if I use a full wave rectifier, after the transformer steps down this input voltage to its bearable level, it will be rectified. If I use a full wave rectifier, I will be getting this type of output voltage which is rectified in both the halves. So after this rectifier, here we will be getting this type of pulsating DC voltage. This is called pulsating DC because it is not purely DC, but we have to get a DC which is constant voltage from this pulsating DC. So what is done here, as we have earlier discussed, we use a filter circuit having a resistor capacitor. We use a filter circuit, and from this filter circuit we get the output as a voltage which is having this type of form. That means it is having ripples, no doubt, but it is in a better form than this pulsating DC. So from the filter output we are getting this ripple. With a ripple we get an output voltage with a ripple. So now depending upon the design of the filter circuit, we can reduce the ripple part. Now this can be assumed to be a DC voltage, or it can be more or less, it can be said that we are getting a DC. But this DC, after we get from the filter circuit, it will be not constant against variation in the supply voltage at the input, or the current drawn by the load, because we are giving this output voltage from the filter circuit, that is a DC voltage, to our load which we want to drive with this voltage. Now if the load varies, that means if we have the variation in the load current due to variation in the resistances extra in the output device, because of this difference or because of this change in the load current, this output voltage will be also varying. Now we have to maintain this output voltage because this load does not want the voltage to be fluctuating. So here is the need for a circuit which is a regulator circuit. A voltage regulator circuit is used after this filter. So this block diagram shows the different stages of our power supply which is regulated one. So we will be now in today's class discussing about this voltage regulator. What is a voltage regulator circuit? What are the different types of voltage regulator circuits that we are going to discuss? So before going into exactly discussing the different circuit components in the regulator circuit, let us in general take the block diagram form of representation of a voltage regulator circuit. And there are two classes of voltage regulator circuit. One is series voltage regulator circuit and the other is shunt voltage regulator circuit. So series voltage regulator circuit block diagram we are showing here, where we are giving the input voltage Vi. There is a control element and the output from the control element is the voltage, which is the regulated voltage. Now there is a circuit which feedbacks this regulated output, that is we are feeding the output voltage through a sampling circuit to a comparator. This circuit is basically made of different resistances, and this sampling circuit feeds back a portion of the output voltage into a comparator. Now as a comparator means it compares two voltages. The voltage is which is coming from the output through this feedback circuit, which is a sampling circuit, is compared with a reference voltage. So there is a reference voltage being given here in the comparator circuit. The output voltage is compared with the reference voltage, and then it drives this control element. The output from this comparator circuit drives this control element, and this control element controls the output voltage to maintain it at a constant level. So what is there inside each block? It depends on the various types of series regulator circuits. Now we will be discussing a very simple series regulator circuit, voltage series regulator, that we are having here. It is having a transistor as the control element. Here the transistor, we are showing here an NPN transistor. This is the control element which controls the output voltage to keep it at a constant level. Now there is a Zener diode also having a Zener voltage Vz, and the reference, as is shown in the block diagram previously, this reference voltage is provided by this Zener diode. Now what is happening in this circuit is that we are having an unregulated voltage at the input Vi. It may vary. The unregulated voltage means that the supply voltage, which is the AC voltage, it can vary, and we want to make the output voltage at stay at a constant level. Even though this input is unregulated, we want the output voltage to be a regulated one. that is done by this circuit. In what manner it does, let us go into analyze that. So the voltage which is at the output, it is obtained against this load resistance RL, and this transistor is the controlling element, and we have a reference voltage given by this Zener voltage of this Zener diode. Now what will be this output voltage? That can be written as V naught equal to, if we look into this circuit, you start from this ground, actually V naught is plus minus is ground, so this will be a loop. Applying KVL, you apply Kirchhoff's voltage law to this loop, starting from this ground and ending again at this ground. This will be completing one loop. So we will be getting then Vz minus to plus, because a Zener diode is reverse biased. So this P should be having connected to negative and should be connected to positive. Now we are having this Zener voltage which is Vz, then this point is base, this point is emitter, this point is collector. So we get minus VBE, voltage between base and emitter, that is this voltage between base and emitter. So Vz minus VBE equal to V naught. In the output circuit we are getting this Kirchhoff's voltage law, that Vz minus VBE minus V naught equal to 0, or Vz minus VB equal to V naught. We get Vz minus VB equal to V naught, or we can write VBE is equal to Vz minus V naught. So now if input voltage increases, then output voltage V naught also increases. There is a fluctuation. Let us consider that at some time the output voltage has increased. Now it is changing, output voltage is changing, and let us consider initially the output voltage is increasing, because supply voltage is increasing, obviously the output voltage will be also increasing. So if V naught now increases, what will happen is that if we look into this VBE, which is nothing but Vz minus V naught. Now Vz is the Zener voltage, it is constant at the value of the Zener voltage. So what will be varying if V naught varies? From this equation it is clear that VBE, base to emitter voltage of the transistor, will vary. So if V naught increases, from this equation itself we can infer, we can see that if V naught is now increasing somehow because of some supply variation, then as negative component of this equation increases, means VBE will be decreasing. So more V naught means if V naught is increasing, then VBE is decreasing. So if VBE is decreasing, what effect on the transistor current? If base to emitter voltage decreases, then obviously the base current will decrease. Similarly, because of this base current decrease, this emitter current will decrease. So IE, which is flowing into the load, that will decrease. So if this IE decreases, load current, which is nothing but the load current, decreases, then V naught will be decreased and it will be brought back to the earlier value. That means V naught will be kept constant. Even though V naught is increasing, then ultimately by this regulator circuit it is brought back. So V naught will be kept or maintained at the same value. Even if we now consider the other way, that when V naught decreases, then also we can see that it will be brought back to its earlier value, because the opposite thing will happen. If V naught is now decreasing, then from this equation it is clear VBE will be increasing. So if VBE increases, this means IB increases, so IE increases, load current increases, so V naught will be again increased, and it will be, that means it will be kept at constant value. So this is a very simple circuit, it is a voltage series regulator. Now another modification of this or improvement of this series voltage regulator is done in this circuit, which is a bit or a little more complex than the earlier one, but it's better. So if we look into this circuit, we can see there are two transistors, Q1 and Q2, and there is another also a Zener diode. Vz is the Zener voltage, and these resistances consist of the sampling circuit, which we discussed or we mentioned in the block diagram. The sampling circuit is formed by these resistances R1, R2. This is the reference voltage Vz. Now what is happening in this circuit? To explain that, let us name the currents flowing in the circuit. Transistor Q2 is having the base current IB2, collector current IC2, and transistor Q1 is having base current IB1 and emitter current IE1, which will be again going into load. Now in this circuit, if we now again find out the relation between the output voltage V0 and the voltage VBE2 for this transistor, let us see what is this voltage V2, which is the voltage across this R2. Now V0 has a voltage division taking place. R1 and R2 are two resistances. R2 is grounded. So if we find out the voltage across this R2, we can find that V0 into R2 by R1 plus R2 is this voltage across R2. Now this voltage V2 is again having in series this Vz. Vz is the Zener voltage across the Zener diode. So now if we apply again KVL in this loop, that is starting from here again ending at ground through this resistance R2, what we get? VBE2, that is the base to emitter voltage for the transistor Q2, this transistor I am considering. So VBE2 plus Vz, you mind the polarities because this is a reverse biased Zener diode, so this point should be negative, this point is positive, and Vz is the drop. So VBE2 plus Vz minus V2 equal to 0. That means we can write VBE2 plus Vz equal to V2. V2 is nothing but the voltage available across the resistance R2, which is V0 into R2 by R1 plus R2. So we can simplify by writing VBE2 equal to V2 minus Vz. From here I am writing VBE2 equal to V2 minus Vz. Now imagine that V0 is increasing because of supply variation in the input supply. The V0, that is the output voltage, is increasing. Now if V0 increases, what will happen? More V0 means V2 will be more, because simply V2 is nothing but the voltage division across resistance R2. The voltage available will also be more if the voltage V0 is more. So if more V2, that means VBE2 is more. So VBE2, that means in the diagram if we look into, the base emitter voltage of the transistor Q2 is now high, more. So if the base emitter voltage is more, that means this transistor Q2 will be having a more base current IB2. So IB2 will be more, and IB2 will be more means the collector current IC2 is also now high. So transistor Q2 has a higher base current as well as a higher collector current. So now what will happen to the other transistor if this collector current is high now, which is the collector current for the second transistor Q2? We have to apply Kirchhoff's current law at this node, at this point. If we apply KCL, sum of the incoming current equal to sum of the outgoing current. What are the incoming currents at this point? We can see here that one current is coming from through R4. So through R4 the current which is coming is, let us name it as I1. I1 is the incoming current, IC2 is the outgoing current, that is the collector current for the second transistor, and the another outgoing current is IB1, which is the base current for the first transistor. So the direction of the base current in the first transistor will be towards the transistor, because it is an NPN transistor, so P must be positively connected, so the current direction will be like this. That means we have here at this point I1 equal to the incoming current equal to sum of the outgoing currents IC2 plus IB1. So if this is so, now as I1 equal to IC2 plus IB1, and just now we have seen that high V0 or increased V0 means more IC2, more collector current in the second transistor. So if this collector current increases, then what will be happening to the base current? Because IB1 equal to I1 minus IC2. So as IC2 increases, base current will be reducing, because I1 does not change, I1 is not changing. Now that means we are getting a lesser base current IB1. So lesser base current IB1 means in the transistor Q1 we will be having the current IE1, that is the emitter current flowing from the transistor Q1, also lesser. So finally we will be getting IE1 less, means the load current which flows through the resistance RL will be less. So V0 will be now less. So the effect of increase of V1 will be finally reducing or decreasing the V0. That means it will be kept constant, or it will be maintained at the constant value. So this voltage regulator is maintaining the output voltage V0 at the same value even though V0 changes, and we have seen that when V0 increases, then it is pulled again down. That means it will be brought back to its original value. Similarly, we can now see, you can think about the other way, or that means when V0 is now decreased, you will find that it will be finally again increased and maintained at the same value. Now another type of series regulator where an op-amp is used for the comparator is shown in this figure. We are having an op-amp, operational amplifier, whose one terminal, that is the positive terminal, is connected to the Zener diode having the Zener voltage Vz, and the other terminal, the negative input, negative terminal, or the inverting input terminal is connected here, and the circuit R1 and R2 is forming the sampling circuit. What will happen in this circuit is that we have to look into the two terminals of the operating amplifier, op-amp. Here this is the positive terminal, this is the negative terminal. The positive terminal is connected to Vz, which is a constant voltage, it does not vary. Other point, which is connected across R2 will be dependent upon the voltage at this point will be dependent upon the output voltage, because what is V2? If we look into the voltage across this R2, this is V0 into, again voltage division like the earlier case, the voltage division is happening, V0 into R2 by R1 plus R2, this is the voltage V2. Now this op-amp is like a comparator, it is a comparator circuit, it is comparing the two voltages which are present at the non-inverting and inverting terminals. So what will be the output voltage from this op-amp? Let us name it as V0 dash. That will be dependent upon the differential input present between the two terminals. So Vz minus V0, Vz minus V2, V2 is this voltage. So this voltage is the differential voltage which is available at the input terminal for this op-amp. So the output voltage V0 dash, which is nothing but the gain of the op-amp multiplied by the differential input Vd, which is nothing but Vz minus V2. Now if this voltage at the output increases, V0 suppose is increasing, what will happen if V0 increases, this voltage V2 also increases, because V2 is nothing but V0 into R2 by R1 plus R2. So if this voltage increases, the differential input, which is the difference between Vz and V2, will be now decreasing, because if Vz minus V2 is the differential input, say Vd, when V2 increases, then the differential input Vd decreases, because the negative component is increasing, means the whole quantity Vz minus V2 will be decreasing. So if this is decreasing, the differential input decreasing, that means the output from the op-amp will be decreasing. So what happens is that V0 dash will be now decreasing, and V0 dash and V0 are almost equal. This is basically, this is an emitter follower, and the output voltage V0 is almost equal to V0 dash, because V0 dash minus VBE is this voltage V0, but VBE is very small, so we can almost say that V0 dash equal to V0. That means now V0 will be also decreased. So what is happening from the whole analysis, we see that even though V0 is increasing, the regulator circuit is acting in such a way that finally V0 is decreased. That means the resulting outcome is that finally the output voltage V0 is maintained at the constant level. So in this circuit, which is using an op-amp as a comparator, we have seen that the change in the output voltage is balanced again by bringing it back to the earlier value, and that can be also verified for decrement of the output voltage. Same analysis can be done in a similar fashion, because if V0 is now decreasing, V2 is decreasing, so the differential input will be now increasing, V0 dash will be increasing, so V0, which is equal to V0 dash, will be now again increased. That means it will be maintained at the constant value. So this type of voltage series regulator circuits that we have discussed is one type of voltage regulator. Other type of voltage regulator which is there is the shunt voltage regulator. In the shunt voltage regulator, as the name is shunt, the immediate thing that comes to mind that it is shunting away some current. That is exactly what is happening if we look into this circuit having the shunt voltage regulator. We are having a diode as well as a transistor, the Zener diode as well as transistor here also. The output voltage is across this load resistance, V0 is across this load resistance RL, and the load current which is flowing in this resistance RL is say IL. IL is the load current, IL into RL is equal to V0, that is the output voltage. Now if we now apply again the Kirchhoff's voltage law here in this circuit, if we see this voltage output V0 and apply in this loop, this is the loop suppose we are considering, starting from this point, then you come to this again back to this point, then what will be the Kirchhoff's voltage law? It will be VBE plus VZ minus V0 equal to 0. VBE, we are starting from this point, so VBE rising voltage plus VZ minus V0 equal to 0. So that means we can write down V0 equal to VZ plus VBE. So that is what is written, V0 equal to VZ plus VBE. Now we can further write it down as VBE equal to V0 minus VZ. Now if now V0 increases, say imagine V0 is increasing because of supply variation, more V0 means more VBE because VZ is constant, VZ cannot be varying because this is a Zener diode voltage. After breakdown this voltage is equal to VZ. What will be increasing is, because of increasing of V0, VBE will be increasing. So more V0 means more VBE. What will happen then if VBE, the base emitter voltage of this transistor increases, then the base current increases. So base current will be increasing, and the base current increases means the collector current increases. So if this current increases, which is shunted away from this total current, then the current which is left to flow in the load will be decreased. This total current minus this IC is equal to IL. So if IC is increased, then IL is decreased. So IL is decreased means V0 will be also decreased. That means we have initially increasing V0, but as increasing V0 shunts away more collector current, then finally the load current IL will be decreasing. That means V0 will be also decreased and it will be maintained at that same level. So this was a shunt regulator using a simple circuit. Another circuit which is an improved version of this shunt regulator, we will be discussing, which is having two transistors. So let me draw this circuit. We have two transistors, they are connected as shown here. We have a Zener diode also. The load resistance RL, this is V0. Now in these two transistors, which are NPN transistors, let us name that is transistor Q1, this is Q2, and input voltage is Vi, and this diode, Zener diode, is having voltage Vz, the load current is IL. Now the transistors Q1 and Q2, the currents flowing in the transistors, let us name as IB2 for this second transistor, IB2, and the collector current for the second transistor is IC2. In this direction it will be, it's an NPN transistor. For Q1, the IE2 for this transistor becomes the base current for the first transistor. This is IB1, which is nothing but IE2, and the collector current for this first transistor is, say, IC1, and the voltage across this resistance R1 let us name as earlier as V2. Now in this circuit, what will happen when V0 changes? Now here also we will be applying again the Kirchhoff's voltage law. What is V0? V0 equal to Vz plus V2, because if we complete this loop, V2 plus Vz equal to V0. So this is the Kirchhoff's voltage law applied in this loop. Now that means V2 can be written as V0 minus Vz. Again, what is V2? Voltage across this resistance R1. If we again apply Kirchhoff's voltage law in this loop, having gone through these two transistors, it will be V2 minus VBE2. This is the base, this is the emitter for this transistor Q2, and this is the base, this is the transistor for this first transistor. So VBE2, if this is VBE2 and this is VBE1, so V2 equal to VBE2 plus VBE1. Now what will happen now if V0 changes? V0 is increasing. For example, we are assuming V0 is increasing. So V0 is increasing means the voltage available across V2, well, voltage available across R1 is increasing, because V0 is equal to Vz plus V2, but Vz is constant, it is a Zener breakdown voltage. So if V0 increases, then the effect is that V2 also increases, having this Vz as constant. So if V0 increases, V2 increases, and as V2 increases means VB1 and VB2 both increase, because there are some increases and these are almost similar type of transistors. So the base to emitter voltage rating for the two transistors will be similar. So if the voltage available V2 is increasing, that means VB2 and VB1 also increase. Now what will happen if VBE2 increases? Then the base current in the second transistor increases, so IB2 increases. So what will happen is, if we write down, say, V0 increases, then the effect is that V2 increases. So if V2 increases, then the effect is that VBE2 plus VBE1 increases. That means the base current in the second transistor increases. Now if the base current in the second transistor increases, then what will happen is that the emitter current in the second transistor, IE2, that is also increased. So IE2 increases, but IE2 is nothing but the base current in the first transistor, because if you look into the circuit, This emitter current in the second transistor is nothing but the base current in the first transistor. So base current in the first transistor also increases, and base current in the first transistor increases means collector current in the first transistor also increases. So IB1 and IC1 increases. So IB1 and IC1 increases, that means if collector current IC1 increases, IC2 also increased earlier we have seen. So the currents which are shunted away are increasing, means finally what is left, load current is decreasing. So IL decreases. Because of increase of IC1 and IC2, the load current IL is now decreasing. So load current decreasing means V0, which is nothing but IL into RL, will decrease. So ultimate effect is that IL, not IL1, IL the load current, IL decreases, so V0 decreases. Initially V0 increased, but finally V0 decrease, means it is kept at constant value. So this is one type of shunt voltage regulator. Now, so the voltage which is maintained constant, if we find out what is the voltage that is maintained constant, V0. So the finally we get that V0 is not changing even though the supply voltage changes. So now if we consider again this series voltage regulator circuit to do an example, let us take the series voltage regulator circuit which was first taken up, having the simple circuit with these parameters given. It is having this transistor. I am again taking up the first circuit that we discussed, having a Zener diode of 12 volt. Let us take this Zener diode as 12 volt, and this resistance R is 220 ohm. Vi is the unregulated supply voltage, Q1 is the transistor, it is having a beta value of 50, say. It is an NPN transistor, and the load resistance RL is 1 kilo ohm. This is the voltage V0, which is the regulated output we should get. So Vi is unregulated, and by using this voltage regulator circuit we should get V0, which is a regulated voltage. Now for this circuit, which is the circuit of a voltage regulator, you are asked to calculate the output voltage V0, and the Zener current, So find out V0 and IZ. So IZ is the current through the Zener regulator. So that is this current actually, IZ. This is the polarities of this Zener diode to which it is connected. It should be the reverse breakdown. So now let us do this example. You are asked to find out V0. Now V0 is the voltage across this resistance RL, which is the current IL into RL. IL into RL will be the V0. Now we have to find out V0. How can we find out V0? V0 can be simply found out if I apply Kirchhoff's voltage law in this loop, because if I apply Kirchhoff's voltage law here, it will be Vz minus VBE, because this voltage between base and emitter of this transistor is VBE. So Vz minus VBE will be V0. So let us find out in that way, it is a simple way to find out V naught. By looking into this circuit and applying Kirchhoff's voltage law in this loop, it is Vz. This is wrong, this is not plus, plus will be here and minus will be here, because this is general diode, polarities should be connected. This is P to be negative and N is positive. So we get rising voltage Vz minus falling voltage Vbe, that is equal to V naught. Vz minus Vb. We know what is Vz, it is given as 12 volt, given in the circuit, and Vbe we all know already. We know that Vbe is the voltage across the base emitter, and that voltage is 0.7 volt for silicon, and it is the standard value taken even though it is not specified. So that means we get 11.3 volt as the output voltage V naught. Now you are asked to find out the Zener current. So this Zener current, in order to find the Zener current, what is this law that we are going to apply at this point? Kirchhoff's current law. So KCL being applied at this point, let us name this current as IR. This current, base current in this transistor is IB. So what will be this IZ? This is the outgoing current. Incoming current IR minus IB will be IZ. So IZ equal to IR minus IB. Now we have to find out what is IR, what is IB, then only we can find out IZ. Now IR can be found out by finding out the potential between these 2 points, Vi minus Vz. This potential is Vz divided by R, 220 ohm, that will give us IR. And IB, the base current, here base current IB has to be found out. So this base current can be found out if we know the collector current IC. IC by beta is base current, but how can we find out the collector current? So collector current is nothing but this current which is flowing through this collector current, and we will be assuming here IC is almost equal to IE, and IE is nothing but this load current. IE is this load current IL, which we already found out. So if we know this IE, or we can also see that IB into beta plus 1 equal to IE, even without assuming IB. By equalizing IC and IE, we can also see that beta plus 1 into IB is equal to IE. So once we know IE, which is nothing but the load current, so if we found V naught, dividing by RL, we will get the load current, and that is equal to IE, and then you can find out what is IB. So IB equal to IL divided by beta plus 1. Now what is IL? IL is V naught by RL. V naught we have found out 11.3 volt. RL is given as 1K. So 11.3 milliampere, because this is 1 kilo ohm. So 11.3 milliampere is the load current, which is nothing but the emitter current, because the emitter current is I, that is flowing into the load for this circuit. And so putting here 11.3 by beta plus 1, 50 plus 1, 51. So 11.3 by 51 will be the base current, and that is equal to 0.226 milliampere. We have known base current. What is the current IR? IR is VI minus VZ by R, and VI is given in this circuit. VI is actually 20 volt. It is unregulated voltage is 20 volt. So 20 volt minus base the diode Zener diode voltage, which is 12 volt, divided by R. R is 220 ohm. So this will be coming in ampere. So the value of this IR is, you calculate this, it will be 36 milliampere. It should come to be equal to 36 milliampere. That means it is 0.036 ampere, and which is equal to 36 milliampere. So we have known IR 36 milliampere, we have known IB, so we can find out IZ. IZ equal to IR minus IB. So 36 minus IB is 0.226 milliampere, and that gives 35.774 milliampere, almost equal to 36 milliampere. So the Zener current is 35.774 milliampere, and the output voltage was found to be 11.3 volt. Now if we consider in this last circuit that we discussed, improved shunt regulator, here what is the voltage at this output that can be found from this relationship. Similarly, if we consider the series voltage regulator, improved series voltage regulator, here we have found out this V2 equal to V0 into R2 by R1 plus R2. So in this circuit, if you are asked to find out what is V0, then we can write down that V0 equal to R1 plus R2 by R2 into V2. And now what will be the V2? V2 is equal to VBE2 plus VZ. So R1 plus R2 by R1 into VBE2 plus VZ. So this is the output voltage. So if we look into the expression for this series voltage regulator, which was using two transistors, then we have an output voltage V0, which is maintained at this value. Now look into this expression for this output voltage, is that for a particular voltage regulator circuit, R1 and R2 are constant, they are not going to vary. Then VZ, a Zener diode, after breakdown, that voltage is also constant. VBE2 will be almost constant at that particular transistor based emitter voltage. So the output voltage V0 is basically constant, that can be seen from this expression itself. So whatever changes occurs in the output voltage, that is just taken care of by the controlling circuit, which is the transistor, and the output voltage will be maintained at a constant value. So if we say, for example, if we take one case where R1 and R2 are given as the 20 ohm and 30 ohm, and you are using a Zener diode having say 8.3 volt. So what is the output voltage? That at what voltage it is maintained? It is 20 plus 30 by 30 into VBE is 0.7 plus 8.3, it is 15 volt. So the output voltage is maintained at 15 volt constant, and the change or fluctuations which may arise due to change in the supply voltage or the load current change, that is taken care of by this transistor. So in today's lecture we have seen how voltage regulator circuit is used to maintain a constant voltage and a regulated power supply which is required for our daily as well as other different uses. That regulated power supply using semiconductor devices like transistors, Zener diodes, we can get an output voltage which is a constant voltage, even though there may be fluctuations in the input supply voltage or the load current. So this is the backbone, this voltage regulator circuit is backbone of the regulated power supply.